Here we are doing integral review part 2, where I know that I will have to learn some new or remember some new strategies of integrals from trig sub to improper integrals, partial fractions, and some applications and reminders down here at the end. The other thing I'll remind you of is, the antiderivative is the function that pops out, and we evaluate that antiderivative between the endpoints, and that's how we get our fundamental theorem of calculus. I know that I'm going to use trig sub on this one, so again, it's indicative of the Pythagorean theorem. When u sub is not available, I set up my triangle in standard position. You see my oopsie from the first attempt on this video, but have no fear. I'm looking at this relationship thinking, well, this is my hypotenuse. This is a squared plus b squared, and it's getting square rooted. So that means my hypotenuse is this x squared plus 9 fella, and I'm going to ignore him as long as I can. That tells me this is going to be a tangent relationship. Not only is this going to be a tangent relationship, tangent is going to be OA. I know that x needs to be in my numerator. I know that 3 needs to be in my denominator. And so I'll do a little bit of my work with tangent on this side. 3 tan theta equals x. That means when I get my differential, 3 secant squared theta is dx. Sounds good. This integral is going to get a little bit messy, but I promise it'll work out. Let's see how this changes. That dx is going to move into my numerator. I lost my d theta. How could I? 3 secant squared theta. My d theta will pop out here, but let's write this denominator that is going to get tricky. 3 tan squared. I know this square root works out every time, so I'm going to have another 9 tan squared plus 9. If this square root doesn't work out, you're either using the wrong method or you've made a mistake. I know this is 9 times tan squared plus 1. I know that's 9 secant squared. I know I'm going to take the square root of that 9 secant squared and get 3 secant squared. So let's move it on to this next, 3 secant when I take that square root. 9 tan squared theta, 3 secant theta, d theta. I know this thing is going to reduce. That's just how it works out. Secant cancels with secant, and now I'm left with this thing. We're going to reduce it out. And we actually had one like this in the first set of notes, except my values were a little bit different, so expect it to turn out fairly the same. I'm going to kind of skip through that simplify because we did it so nicely last time. I promise it'll work out the same way. I'll pull out the 1/9, and what I'll see is that the secant and tangent kind of reduce just a little bit to set up a nice u substitution, where once again u would be sine because that's my innermost and it's my most complicated, where du would be cosine theta d theta. So not only do I have a trig sub on this one, I also have a u sub inside of my trig sub to sub this thing out to get a nice clean integral of 1 over u squared du. Now I can just anti-derive this thing, and I'd get 1/9 u to the negative 1 plus c. I'm going to plug back in that u to get my nicest, cleanest answer, where I would have 1 over sine theta plus c. The reason I do that's this u over negative 1 is 1 over u. So I write it this way because then my eyes get to see, hey, this is 1/9 cosecant theta plus c as a final answer. Right? I'm going to start this next trig sub, but since we did 4 on the last sheet and we're doing 2 here and you practiced and did your homework in between, I'm not saying it's a waste of my time, but it's not the best use of your video time to do this. So once again, I'll draw a nice triangle. I see this as a subtraction relationship. A subtraction relationship means this describes one of my legs, which means 1 is my hypotenuse. Alright, if 1 is my hypotenuse, that means I want to pick x as one of my legs. This could be an OH would be really nice. I could even do secant, but I don't want to do secant because secant's yucky. I'm going to put this over here to get a nice clean OH. Alright, that means I have this square root over here. And now we go sine theta is over h, x over 1. This one works out really well. When I take my derivative to get my differential, I'm all ready to go. I didn't even have to carry a constant because I got a nice 1 here. And so when I work to simplify this thing out, I need to move my bound. What are you doing? Right? Over here my bounds are x equals 0 and x equals 1. So when x equals 0, sine equals 0, or theta equals 0. And when x equals 1, well, that's at pi over 2. And so I'll move my bounds along with that. From 0 to pi over 2. Now the rest plugs in nicely. This is sine squared theta. My d theta is taken care of. My square root becomes 1 minus sine squared theta. Well, would you imagine that becomes a beautiful cosine squared? And so I've got this becomes a cosine squared. I know I square root it. 0 to pi over 2. Sine squared over cosine. And I bet none of you called me out for making that mistake while you're watching the video. You just blindly believe in I'm making every step correctly. Look, I misreplaced my differential. Oops, this should be a cosine theta d theta. So I would have times cosine theta d theta over here, which reduces this cosine. I get a nice integral from 0 to pi over 2 of sine squared theta d theta. Use a little bit of substitution. I believe in you to do these steps by yourself, but you come out with the nicest, cleanest answer this side of August. Pi over 4. Beautiful. Now we're getting into some improper integrals again. Improper integrals are when I'm dealing with these infinite asymptote looking things, and I'm just going to do a little bit of limits to help me evaluate something at infinity. Now this first one is a little bit of both. This is just keeping you on your toes here, folks, because not only that, I'm also going to have u equals square root of x. Right? I see x, square root of x, square root of x, that immediately is telling me, hey, I should probably do a u substitution. And I'll do just that. That means this integral changes. Let's move the bounds to when x equals 0, u equals 0. When x equals infinity, u would still be infinity. And that's probably not the most proper way to write it. But yep, there's my fixed bounds. Is u from 0 to infinity. This becomes e to the power negative u du. How beautiful. Anti-derive this thing and just keep moving on with our life. So what I'm going to do is I'm going to set this top bound equal to b. And I'm going to use a limit to evaluate it. My limit as b approaches infinity, this integral now changes from 0 to b of this simple integrand. Now I'll use that integrand, or I'll take my antiderivative, and the rest of this will all work out nicely for me. Oh, did I do that too? No, that's shameful. This should be a 2. This should be a 2. Yeah. So then I would get 2 times this antiderivative. It would be a negative 2, e to the negative u. Don't mind my terrible writing here. And I still need a limit over here. B approaches infinity. That's shameful that I made that yucky, but we're going to power through anyways because I gave you some great trig sub stuff at the top. Now when I evaluate this, this will become negative 2 e to the negative b minus negative 2 e to the negative 0. And again, this is still, I'm carrying this limit all the way through because I haven't evaluated what b is yet. I cannot drop that limit notation until I've plugged in or evaluated that limit. As e goes to the power negative infinity, I know this thing just goes to 0. And so this just simplifies here. Negative of negative e to the negative 0, well, that just becomes 2. What a nice answer. Over here, we're dealing with the same thing, except I have a discontinuity at 1. So instead of approaching infinity, I'm going to approach 1. Again, a nicer way to write this integral is probably from 1 to 2 of x minus 1 to the negative 1/3. It's going to just help me with my antiderivative, my anti-power rule in my head, and now I'll do that limit substitution. In this case, it's going to be a limit for a as a approaches the right side, and I'm choosing the right side because I'm going from 1 to 2. Right? This thing exists on either side of 1, but we want the positive side to approach 2, and I will make my bounds and keep this the same. I do my antiderivative. It would put me to 2/3, so I get 3 halves x minus 1 to the 2/3 evaluated from a to 2. Alright, I know that as I plug in, oh, this just becomes nice, right? I got rid of my denominator. I'm not afraid to divide anymore, so this just works out nicely. 3/2 times 2 minus 1 to the 2/3, that's 1 to the 2/3, that's just 3/2. I'll plug in a now, right? This is still a limit. It's going to be no longer a limit because I'm going to plug in that value of a. Minus 3/2, 1 minus 1 to the 2/3. That's 0. So my final answer out here ends up being 3/2. Sorry for the bit of mess on that page. Sorry I'm dropping my limit notation. I should be better than that. But this is a skill you've seen before, just a nice refresher that you need to carry that limit through on those discontinuities or those infinite limits, because that placeholder will allow me to evaluate these various points or at least get through the integral. Everybody's favorite partial fraction decomposition over here. Again, it just goes to say that, hey, if I know this fraction is built up, if this denominator is built up of these two components, therefore there must be a fraction decomposition that exists that allows me to do this. Right? If these are the components of my denominator, this numerator has to become separable into two separate fractions. And when I kind of cross multiply these things, I would get a times x plus 1, b times x minus 2. Again, I'm only looking to do this skill when I know my denominator is separable, that my denominator is factorable, and now this whole thing would be equal to 1. Right, because I'm cross multiplying as much as I'm going x plus 1, x plus 1, x minus 2, x minus 2. All right, so my terms that lead to x is ax plus bx equals 0x. 1 times a minus 2 times b equals 1. This is for x, and this is just for my constants. Now I can solve this system of equations. I know I already taught you how to do this. We talked about substitution often, but I'll just go elimination here. It's going to work out pretty nice. 3b equals 1, so b is 1/3. Well, if I know b is 1/3 and a adds to make, that means a is negative 1/3. That means I can pop those back in up here, and this integral becomes computable. This would be negative 1/3, and I'm going to again do a little fraction magic here, x minus 2 to the negative 1 dx. Here I'll have plus 1/3 x plus 1 to the negative 1 dx. And you say, why would you possibly want to do that? Just because I like these negative ones. It reminds me a little better. I'm not searching for some other thing. I'm not figuring out how I carry that 1/3. But at this point, your integral skills are strong enough to finish this thing out. I know these both becomes natural logs. So I get negative 1/3 natural log of the absolute value of this thing, evaluated from 3 to 4. And I know that I would also get plus 1/3 the natural log of this thing, also evaluated from 3 to 4. I'll plug in all my values. I'll simplify it out here. I believe in you to get all the way there. If you use your log rules to the fullest extent, 1/3 ln 8/5. And I love log rules for that reason. All right, onwards and upwards. I'm looking to do some area and application. Now that you've done all of your integration skills, let's look at 1, 2, 3 different ways that they're useful. Area between a curve is extremely useful. We'll do it ourselves, right? That's part of the reason why we did the systems of equations, to find those intersections, define them, and get there. Again, this is y equals ln x and y equals 0. As much as I would love to do the integral of ln x dx, I know you all love that so very much, there's an easier way to go about this, right? I don't want to integrate ln x. Rather, let's solve this thing for y. And now let's go stars and stripes. Let's do our integral this way, where I have a top minus bottom situation to solve this area. Sorry, I had a moment there where I questioned everything in life, right? I could definitely do this dx, but I wanted to show an example dy. So where I will see this kind of happening is that I'm trying to find this area. It's an upper minus lower. So my integrand, right, this curve here I just defined as this. So my integral looks like this. It goes from 0 to 2, because I know this coordinate is 2 comma e squared. That should be obvious. Now, the upper is e squared, the lower is e to the y, and now I'll just integrate this thing. It'll work out just fine. This becomes e squared y minus e to the y, evaluated from 0 to 2 with an antiderivative, because e squared is just a constant. I throw in some values here. That's 2e squared minus e squared minus 0 minus 1. Just simplifying a little bit here, I get e squared plus 1. Again, I definitely could have done this dx, but I wanted to show an example dy, and unfortunately, in hindsight, I don't think that was my best dy example. You didn't hear that. Onwards, some more area between curves, some top bottom. Again, some good things here. I'm just trying to get you to think about these shapes. Instead of y equals x squared, we have x equals y squared. So it is a parabola, but it opens to the right because it's kind of changing who's independent and dependent, but I have my positive positive and my negative positive. I'm plugging in y values and I'm getting out x values, and here again I have a line, and this line will work out just fine. I believe in you to figure out how to plot this line. I don't know if you have to punch in coordinates or what. Again, I have to think about the bounds on this area and how I would accomplish that. Over here I have 1 comma negative 1. And then up here I would have 4 comma 2. A little bit backwards from what we're used to, but definitely something we're capable of. And again, the area between curves here, I can't do dx, because if I did dx, it would fail at this moment where I'd find the area between the curve and itself. So what I need to do is go dy, where the linear is my upper and the parabola is my lower. Do a little stars and stripes to get this to go. The linear is my upper. The other one is my lower. I need my bounds. My y values are going from -1 to 2. You would make me extra happy if you wrote y equals -1 to y equals 2, because it'll just be good practice for later in the year. Alright, and we'll just do our antiderivative. I'm going to reorganize this stuff a little bit, but at this point I shouldn't have to show you anymore, because you guys are very capable of this. Right? But the setup and the picture and the mental image is really what matters on these types of examples. Area between curves, weird functions you're not used to, and this exact type of setup would be really useful and really helpful as we get further into Calc 3, because being able to define this region, integrate over this region, bounds of this region is an impossibly, amazingly important skill. Last but not least, we have curve length. Again, the concept behind curve length is that I have this curve, and I can break it up into infinitely small pieces where I have my dx change, my dy change, and I could measure this length. And again, this is just Pythagorean theorem. L would be the square root of dx squared plus dy squared, right? A squared plus b squared equals c squared, and square rooted across. But dx, the amount the x changes with respect to x is just 1. So that's where that 1 kind of drops in our formula, and so that change is really dependent on y. It's not just 1 for no reason, it's because dx is this portion of the triangle, and that fraction, quote unquote, differential reduces to 1. And I'm just going to keep repeating this for whatever my bounds a to b are, and I'll integrate this operation over the whole region to grab all the little curve lengths to then get a large curve length. Again, I've set up a nice example for us here where I see this from 1 to 4. I'm just plugging in the things. I do need dy dx, so I will take a little derivative here. Reciprocal here ends up at 1, and so I would just get this, or the square root of x minus 1. And so when I plug it into this curve length from 1 to 4, I would get 1 from the dx, and the square root squared just gets me this. Well, that actually works out really nice. I just get the square root of x dx. And I can integrate that really easy. 14/3. All right. So that is the end of integrals for us for now, but I promise second semester will be almost all integrals for us.